Right, so whenever we look at our elements, we want to kind of break that down even further. So all matter, right, whether you're looking at hydrogen on the periodic table, oxygen, or any other element on the periodic table, they're all made of atoms, right? And then furthermore, we can break that down even more to say that atoms are composed of 3 different subatomic particles. So we're going to look at these subatomic particles, which are going to be the proton, the neutron, and the electron, and each of them have their own individual properties. So a proton is positively charged, so it's going to have a +1 charge. A neutron is neutral, so it has no charge. And an electron is going to be negatively charged, so it's going to have a -1 charge. So we can also look at the masses of each of these, and you can notice these numbers here kind of have significantly small numbers, which is why we're using it in scientific notation. So a proton and a neutron are both 1.67 times 10 to the -24. And if you look at what I did is I kind of read both of those numbers to 3 significant figures, 1.67 and then times 10 to the -24. So both of those actually have the exact same mass if we were only to read it to 3 significant figures. Now if we go out to 5 significant figures, we could say that the neutron is slightly larger. But that's like saying, that'd be similar to saying, right, you have one person who weighs 200.0 pounds, another person who weighs 200.0 pounds, so they basically weigh the same, but one person could say, well, I weigh 200.001 pounds, and someone else just weighs 200.000 pounds, right? So is that, you know, those extra significant figures really matter that much? No, they pretty much weigh the same thing. And the reason I kind of point that out is if you go to this last column where it mentions the mass, in this what is referred to as the AMU. So AMU refers to atomic mass units. So atomic mass units are kind of like an arbitrary scale. So basically, one atomic mass unit is 1.67 times 10 to the -24 grams. Right? So what we do is we say that both protons and neutrons have the same mass in terms of atomic mass units, and we say they both have each weigh 1 atomic mass unit. Now, if we go down to the electron, right? So the electron, you can see here, has a mass that's 9.1093 times 10 to the -28 grams. So this means it's going to be much smaller in mass than either a proton or a neutron. Remember, with a negative exponent, the larger the negative exponent, the smaller the number is. So an electron is about 1,000 times smaller than a neutron. So we say its mass is negligible, right? So the example here is, let's say one of us steps on a scale as a person, and we weigh, say, 150 pounds, right? And that's our weight. And now we step on a scale again, but this time there's an ant crawling on our leg, right? And let's pretend it's not a fire ant that's going to bite you, so you don't even notice it, but there's an ant crawling on you. You're still going to weigh the same 150 pounds. That ant's mass, the ant has a mass. It's just very, very, very small compared to the weight that we weigh. So we would say that the mass of the ant is negligible in the overall weight. And that's kind of how electrons are. Whenever you put the protons and the neutrons and electrons together, the overall contribution to the weight of an atom due to an electron is negligible. It's not going to have any impact. All of the weight in an atom is really going to come from the protons and the neutrons. All right, so here's what an atom looks like. Well, not really, but this is kind of a cartoon diagram of what an atom looks like. And you can see, if you look at this closely, you notice that there is like a kind of a cloud sphere that goes around here, right? So that sphere is going to be the overall size of the atom. And most of the size of the atom and most of the volume of an atom is in this, what we call the electron cloud. So that electron cloud is going to be that bluish, grayish kind of sphere that we kind of see here that goes around and around, right? So this is going to be kind of the main part in terms of the volume of the atom. However, in the very middle of that electron cloud, there's a dense core that we call the nucleus. So over here, it kind of shows you a zoomed in view of the nucleus. And inside the nucleus is where you have your protons and your neutrons. So if you remember, right, the neutrons and the protons are what have all of the weight. So we say that that dense core is from the nucleus, and that's where most of the mass is. And I say most of the mass, pretty much all of the mass. We just don't want to sell the electrons short. They still have mass to them. They're just negligible in terms of how they relate to the protons and the neutrons. So most of the volume of the atom comes from the electrons, right? And most of the mass comes from the protons and the neutrons, which are in the middle. And kind of an analogy for this is like if you imagine like a big baseball stadium or a soccer stadium or a football stadium or something like that. So if you were to go to Raymond James Stadium to watch the Bucks play, and you were to put like a baseball or something kind of in the middle of that field, right? That would be the size of the nucleus. And then if you take the rest of the field, the stands, the parking lot, kind of that whole area around it, the rest of that is going to be what the volume is. Now it would be the electron cloud. So that dense core in the middle where all the weight is would be that baseball kind of in the middle of the stadium, and then kind of all of the sidelines, and then the stands and the bathrooms and the concession stands, all of the rest of that stuff would make up the volume, which in this case is or where the electrons would be. All right, so hopefully that analogy can kind of help put it into perspective. If you look at the actual sizes, it says the nucleus is about 10 to the negative 15 meters, and the electron cloud is 10 to the negative 10 meters. So that means it's a 100,000 size difference. So 100,000 times, the electrons are 100,000 times bigger in terms of the volume they occupy than the nucleus, which is where the protons and the neutrons are found. When we look at the periodic table, right, every element is going to be on there with their symbol, and then above that symbol is going to be a number, and that's referred to as the atomic number. So that number kind of keeps growing like with each element. So like the element 1 is hydrogen, 2 is helium, 3 is lithium, and that is going to keep going up 1, 2, 3, 4, 5, and it's going to keep going up sequentially that way. That atomic number refers to the number of protons in the nucleus. So what that means is that every atom of a given element, so all lithiums in the world are going to have 3 protons in the nucleus. Okay, all hydrogens in the world are going to have 1 proton in the nucleus. All carbons are going to have 6 protons in the nucleus. Right, so you can kind of go through looking at the periodic table, and whatever number that is above the element is going to tell you how many protons are in the nucleus. Now, every atom is going to have that number that tells us the number of protons that are there in the nucleus, and that means that different elements are always going to have different atomic numbers. So for instance, lithium is going to have number 3, hydrogen is always going to be 1. So you can't have a hydrogen that has 3 protons. If you start adding protons to it, you change the element that you're talking about. All right? So different elements are going to have different atomic numbers. The last bullet point on the slide says that a neutral atom has no net overall charge. So that means that the number of protons is always going to equal the number of electrons. So in the next chapter, whenever we get to chapter 3, we'll talk about things that are called ions that have charges, and that's where the number of protons and electrons are going to be different. But whenever we're talking about a regular atom or regular element that we're looking at on the periodic table, they're always going to be uncharged, which means that the number of protons have to equal the number of electrons. All right, so if something has 6 protons, there have to be 6 electrons there to balance out that charge so that that overall atom is going to be neutral. Another important characteristic of atoms is their mass number. So whenever you look at like in this case, the hydrogen, the carbon, the nitrogen, and the oxygen, from their atomic number, we know how many protons they have. So the number of protons are always going to be constant, right? Because that's what we're going to see whenever we look at the mass number, right? So 1, 6, 7, or 8 for oxygen, right? So those numbers are always going to stay constant for a given element. However, the thing that can change is going to be the number of neutrons. So the mass number is going to be the number of protons plus the number of neutrons. And as you probably can figure out, the reason we don't include the number of electrons in the mass number is because their mass is negligible. All right, so if you look at hydrogen here where it says hydrogen with a 1, that 1 refers to the atomic number. The atomic number is going to be the same as the number of protons, which you can see down here. So this 1 refers to the number of protons. Because the atomic number is 1 and it has 1 proton, we also know that the number of protons have to equal the number of electrons, right? Because, again, everything we're looking at right now is going to be a neutral atom. So the number of protons have to equal the number of electrons. Now, the mass number, which you can see here, it says is also 1. Well, that means that if the mass number is 1, that means there's a total of 1 proton and neutrons. Well, if we know we have 1 proton, that by definition means that there has to be a total of 0 neutrons, right? So the mass number does not show up directly on the periodic table because different hydrogens can have different masses. Different carbons can have different masses. We'll talk about how we look at those when we talk about isotopes coming up here in just a minute. All right, so for carbon, we know that carbon is always going to have the atomic number of 6. And what this is saying is that, okay, if the carbon, we know it has an atomic number of 6, and if carbon has a mass number of 6, how many protons, electrons, and neutrons are there? All right, so based on the fact that the atomic number is 6, we can say that there's going to be 6 protons. Because there's 6 protons, there are also going to be 6 electrons. Now, for the mass number of 12, that means that the mass number, so using the formula at the top of the screen, that means the mass number is 12 is going to equal to the number of protons, which is 6, plus the number of neutrons, which I'll just put here as an n. So we could solve for n and say n has to be 6, and that's where the number of neutrons comes in. So again, in order to do this, we have to be told what the mass number is. So you can do the same thing here for nitrogen and for oxygen, right, given those specific mass numbers. Okay, so the idea of an isotope is to say that there are some elements that will have a different number of neutrons. So here's an example with chlorine. So actually, before I go into the example, the way this is written here is chlorine, that's the element symbol. The mass number is written here in the upper left, and the atomic number is written down below. The mass number always has to be greater than or equal to the atomic number, because remember what these mean. The atomic number is the number of protons, right? So 17 is the number of protons, and the mass number is going to be the number of protons plus neutrons. So it is possible for something to have 0 neutrons, like we looked at on the previous slide with hydrogen. But since the mass number includes the number of protons, that top number always has to be bigger. I could write this exact same expression without giving you the 17. And the reason for that is you can always look up the atomic number on the periodic table. So let me go back to an earlier slide I have. And if we look at the periodic table here, well, here's chlorine, right? So chlorine, I'll go ahead and make a box around it. Chlorine has the number 17 associated with it on the periodic table. That number 17 refers to the atomic number. That atomic number refers to the number of protons. So anytime you have chlorine, there's going to be 17 protons. So even without the 17 on this other slide, you should still be able to figure that out. So that said, it's all here. And now let's go ahead and look at the problem, right? So if you were given that expression, chlorine with 35 as a mass number, 17 as the atomic number, or like I say, even if you weren't given 17 for the atomic number, you should be able to figure that out. How many protons are there? There's going to be 17. How many electrons are there? Well, again, it's neutral, it has to be 17. to figure out the number of neutrons, right? You're going to take the mass number minus the atomic number, and that's going to tell you how many neutrons there are. Now, if we look at the example on the right, it's still a chlorine. The atomic number has to be the same. The atomic number for all chlorines are going to be 17. However, the mass number here is going to be different. So the mass number, being this 37 number, is going to be different, and what that means is we have a different number of neutrons. So in this case, we're still going to have 17 protons, we're still going to have 17 electrons, but the number of neutrons is going to be different, and because there's going to be more neutrons means we're going to have a greater mass. So again, isotopes end up being atoms from the same element, right? So both of these are chlorine that have a different number of neutrons. Now, looking at the periodic table, you will see on any given symbol, you'll see the symbol, right? And you'll see the atomic number above it. And beneath the symbol is going to be something that refers to the atomic weight. So the atomic weight is a number that is given in atomic mass units, and that number is going to be a weighted average of all of the isotopes that are there. So to explain this, I want to go and give an example. So let's say I'm going to make up something that's not even on the periodic table. So let's say we have an element that's called X, right? And let's say that X has a mass of 10. So a mass number of 10. And let's say that though X can also exist as a mass of 11, and X can also exist as a mass of 9. So there's 3 different forms of X in the world. There's X that weighs 9, there's X that weighs 10, and there's X that weighs 11. All right? And those are the only 3 forms of X that exist in the whole entire world. So you go out in the whole entire world and you kind of figure out that there is an equal mix of all of these X's. So in other words, I go through and there's 33.3% of that one, there's 33.3% of that one, and there's 33.3% of that one. So right, the overall relative abundance of all of those are going to be 1/3. So if you were to take an average, right, they're all going to average out because you're going to have basically 1/3 of the mass is 9, 1/3 of the mass is 10, 1/3 of the mass is 11. The overall average for that would be 10. Okay, so in this case, the overall mass is going to be 10. All right, so now let's do a different example. Same X, but now you go out and sample in the world, and 99% of it weighs 11, and there is 0.5% each for the other 2. So basically, in this situation, pretty much all of the X that exists in the world is going to weigh 11 atomic mass units. Well, in this case, the overall weighted average of those is going to be really close to 11. So I'm just going to do approximately 11. It would really probably be like 10.99 or something like that. But you get the idea. Because it's almost all of it is 11, it's going to weigh 11. Now, we could do the other example where we had 99% here, 0.5% of the others, right? And in this case, the overall weighted average is going to be approximately 9. So another way to think about this is like your grades, right? You've always had classes where, you know, your final exam might be worth 50%, and then a particular quiz might be worth 10%. And you can do a weighted average of all of your grades, and like your final exam is worth more. It's the same idea here, right? If there's more of, say, this one, where we're looking at 99%, right, that the overall mass is going to be closer to 11 in that particular case, right? So again, weighted averages are how we get to this overall atomic weight that you see on the periodic table. Okay, so looking at these 2 examples, right, there's a number of questions there. What's the atomic number, the mass number, and then the number of protons, neutrons, and electrons? All right, so for the one on the left for carbon, the atomic number, right, refers to the number of protons, and that's going to be 6. So again, that number we get because it's the lower number here, and that's the one that can also doesn't even necessarily need to be written there because we can look at that on the periodic table. The mass number is going to be 13. That's a number that has to be given to us. That's the larger of the two numbers. The number of protons is going to be the same as the atomic number. The number of electrons is going to be the same as the number of protons because it's neutral. Now the number of neutrons is the mass number minus the number of protons, right? Because protons plus neutrons has to equal the total mass. So in this case, it would be 7. All right. Now, if we go over and look at SB here, right, the atomic number is going to be 51. The mass number is going to be 121. The number of protons is going to be the same as the atomic number, which is going to be 51. The number of electrons has to be equal to the number of protons because, again, this is neutral. Then the number of neutrons, right, we calculate by taking the mass number, subtracting it from the number of protons. So in this case, 121 minus 51 gives us 70. All right, so that's how you would do these types of problems.